Welcome back, Shreyansh this side, and today we are going to do database indexing. Mostly database, when I say it's a relational database management system, which we are going to discuss. So this question has been very frequently asked, database indexing. So I will share you my understanding of how database indexing works. Okay. So before we start even discussing the indexing, right, we have to first understand these three things, right? How actual the table data is stored. First thing that should be clear, how table data rows are actually stored, what type of indexing present, understanding the data structure used for indexing and how it works, right? So once we have this three better clarity, then only we can understand how DBMS make use of all these three things and able to perform the indexing. Okay, so one thing first, I would tell you that so whenever the tables which you have, let's say you have a table, this is row, this is column, right? And you have a data 1, 2, 3, 4, A, B, C, D, right? So generally, what question or what whenever the indexing come, generally what engineer might be saying that okay, we will create an index on this particular, let's say we are doing an indexing on this particular column, so we will create an index 1 2 3 4 5, right? And it will point to this rows, right? And any query will happen, it will happen on top of it, it will able to fetch faster. Okay, you want 4, so on this index it will able to find the faster, and it will goes to point to the particular row. Okay, so what I'm trying to say is that this is very high level. But today we are going to step down into one level deeper, because that's where the interview follow-up questions asked. Okay, so now let's go into little bit deeper, and I'm not going to shut down or cut down this video shorter, because if even if it is go little bit longer, I will continue to it. I will not do any trimming for sure. Okay, so let's first discuss how data is actually stored. Very important. So now let's say this is your table. You have a row 1 2 3 4 rows and 3 columns, and let's say these are the 3 columns: employee ID, name and address. So this is generally a very you can say that typical table, let's say employee table. So this is just a logical representation. This is just a logical representation. This is not how actual the data is stored in the DB, right? This is just a logical representation, not a physical representation. Remember that. Okay. So when we say that, hey, Shreyansh, this is logical representation, then how the actual data is stored? Okay. So now let's say in our table we have this data, 4 rows, 3 columns. So what DBMS will do? What DBMS will do, database management system, what it will do, it will create data pages, right? And one data page generally of 8 KB in size, depends upon what DB you are using. Okay, but generally the size of one data page is 8 KB. Okay, each data page can store multiple table rows in it. Okay, so now we know that this is just a logical representation. These rows are actually stored in data pages which DBMS creates, right? How? So this is how a typical data page looks like. So when I say that it's a 8 KB, so in 8 KB how many bytes are there? 8192 bytes. Okay, now 96 bytes are reserved for the header. In a header, what generally information it have? It has page number, how much free space this page has, checksum and etc. Okay, so header information, I would say that it has very basic information like page number, free space, checksum, etc., which is 96 bytes. After that, 806 bytes, 8060 bytes are totally reserved for data records. When I say that data records, it is actual the rows. So here the actual the rows will be stored. So actual data is stored in here. And last 36 byte is known as offset array actually. So what does offset contains is it's contain an array, and each index of an array holds a pointer to the corresponding data in the data records, right? So in this data page, this is an header. Let's say it has the pages row 1 data, row 2 data, row 3 data. Let's say only 3 rows are there. In this offset there is an array 0 1 2 3. So 0 will point to, let's say, row 1. 1 will point to, let's say, row 2. So what I mean to say is that this offset array contains a array of, you can say that, a pointer, and this, what it point to, it point to the actual rows. Now you can ask me, hey, why we need this offset array? We will see that how it helps DBMS. But don't worry. First of all, what I want you to understand is how data page looks like. So one thing, very basic thing you should know is DBMS creates data page, and inside a data page, the rows are stored. Okay, so that only you should understand at this point of time, and don't worry about the offset array. We will see with an example and how DBMS make use of it. Okay. So offset is just an array of, you can say that, pointer to what? Pointer to the particular row inside a data records space. Okay. So total 8 KB data pages, and out of this 8 KB, 8060 byte is actually there for the rows or actual data, and rest is for header and offset array. Okay. So now it's clear that these rows which we are creating, it looks like it is creating, it's stored like a table, but actually it is going here in the data page. So now let's see this. So if one table row is, let's say, 64 bytes. So now let's say this row 1 is of 64 bytes. So this is, let's say, I'm just saying hypothetically, let's say it is 16 bytes, right? This is also 16 bytes, right? This is 32 bytes. I'm just saying, and it all combined to 64 bytes. So one row is your 64 bytes, right? And we know that for storing the rows, how many bytes it is available in a data page? 8060 bytes. So 8060 divided by 64, so almost around 125 it comes. So means in one data page, if it is a size of 8 KB, then we can store 125 DB rows in it, right? If one row is of 64 bytes and one data page is of 8 KB, then we can have 125 DB rows in it, right? And how data pages generally look like? So we have header. So I have just kept for simplicity only page ID or page number, like 1, right? And then the second part is your data record. Data record which actually holds the data, the way the row is inserted into a table or by a user. In the same way, generally the rows are inserted. So user has inserted row 1, so it has inside this, it put row 1, row 2, row 3, row 4, row 2, row 3, row 4, and if let's say it has added 5, row 5. Okay, like this it will add. How many it can store? 125 DB rows it can hold. Then what is the third step? Third step, I told you, it's an offset array. So here I have created an offset array. Okay, so this offset array has index like an array 0, 1, 2, 3, 4, 5, right? 0, 1, 2, 3, 4. So 0, it is pointing to, let's say, row 2. This 1 is pointing to row 4. 2 is pointing to row 5. 3 is pointing to row 3, and fourth index is pointing to R1. Okay, so what does offset array hold is, now it's clear, it's an array, and this array actually contains a pointer to what? The actual data which is present inside this data page. Now you can ask me, right, hey, what is this ordering? At 0th index R2 is stored, right, and at 4th index R1 is stored. So doesn't make sense, right? It is not ordered, not increasing order, not decreasing order. What is this order, right? So don't worry about that part, because when I will come to that, then it will make sense better how DBMS is make use of offset array. But now you should be clear with this, that how your data is actually stored by a DBMS. So this table is actually visible to you, but for DBMS, the way it is stored is like a data page. So for each page it gives a number, and it stores the data in a page, right, in this data records area, right, and for each this rows there is an offset. It also maintains the offset also, where it put a pointer, and the ordering DBMS will decide when we discuss about indexing. Okay, till now it is clear, right? All these numbers which I am saying, 8 KB, 64 bytes, that depends, right? That depends upon DB to DB. So, but for this one, this is the most common. Generally, you will see data page is 8 KB. Cool. So till now we know that, okay, this table, how it is represented in one page. So DBMS, remember that DBMS creates and manages this data page. So this page, whichever we have talked, who managed it? DBMS. So total control over the DBMS. So for storing one table data, it can create many data pages. So now let's say this table grows and it contains, let's say, row 10,000, like row 10,000. So definitely 10,000 rows cannot come into page 1, right? So it's upon DBMS only to create multiple pages. It will create page 2, page 3, page 4, or page 100, and keep on storing the rows in it. Okay, so DBMS creates and manages this data pages, and for storing one table data, it can create many data pages. Okay, I know that the very big questions coming to your mind, hey, if there are 100 of pages, how DBMS gonna manage it, right? We will come to that one. But for now, for simplicity, a table data is generally stored in a data page, and one data page is full. DBMS can create more data pages and keep on storing the table data. Till now, very basics we know. Now, where these data pages ultimately get stored? These data pages ultimately get stored in the data block. Now, this data block is actually a physical memory. This is actually a physical memory, right? Like disk. On a disk, there is a, so you know, right, disk, and then there would be some sector, track. So there would be one data block. You can say that data block. So what does data block means? First understand what is data block means. So data block is the minimum amount of data which can be read and write by one input output operation. So you can say that this is the minimum amount of data which one IO operation can read or write, right? So this is the minimum amount of data which you can fetch in a single shot, or which data blocks can have one IO operation. Okay, and who manages this data block? It is managed by the underlying storage system. Let's say like disk or SDD, let's say, if it has data block. So it is managed by storage system, underlying storage system. So remember that data block is not managed by DBMS. It is not managed by DBMS. It is managed by storage, underlying storage system like disk. DBMS manage only data page, right? So whatever the data you have to put into somewhere into the memory or disk, right? And inside a disk, what ultimately we have is data block. So these data pages which DBMS creates, who creates it? Which DBMS creates, ultimately get stored where? Inside a disk or inside a memory, right? Inside a disk. So it is stored actually in the data blocks. And DBMS has no control over this data blocks. It can be scattered. So now let's say if this disk has thousands or millions of data blocks, let's say, DBMS has no control that, okay, my page 1 goes here in this data block. My page 2, for example, it can go into this data block. Data block, let's say 100. Data block, let's say 1. So what I'm trying to say is that DBMS only has control till data pages. It can decide what data I can store into this, what rows I can store into a particular data page, right? But when it is writing to the actual disk memory, right, then it ultimately gets stored into a data block and it has no control over it. Okay, so now you know what is data block. It is the minimum amount of data which can be read and write by an input output operation. So data block size can range from 4 KB to 32 KB. And most common size is 8 KB. So now let's say your data page which DBMS manage, it is of 8 KB. Data block which actual stores the data in the like a physical location, it range from 4 KB to 32 KB. But most commonly you will find is also same like an 8 KB. So if it is 8 KB means one data block stores one data page only. But if it is, let's say, 32 KB, then it can store multiple data pages. Data page 1, data page 2, data page 3, right? So one data block itself can store multiple data pages. Okay, so based on the data block size, it can hold one or many data page. Okay, now there is one more thing is DBMS maintains the mapping of the data page and data block, because I told you that DBMS has no control over the data block where this particular page, where the data page is stored. It has no control over it. So that's why it maintain a mapping. That's why DBMS maintains a mapping that, hey, data page 1 goes into this address, data block 1. Data page 2 ultimately goes to this address, data block 1 itself. So it is possible that one data block, this is, let's say, data block 1, one data block can hold multiple pages. Data page 1, data page 2 is stored in the same data block because data block size can be higher than the data page, right? So DBMS maintains this mapping that, okay, this my this page, because DBMS maintain this page, right? Okay, this page 1 is stored in this block, this page 2 is stored in this block, this page 3 is stored in this block, right? Like this. So remember, DBMS controls the data page, like what rows goes inside in which page or sequence of the page, etc., but has no control on the data block. Data block can be scattered over the disk. Okay, so I think you should be clear with till now the first part, how the table data actually is stored in the DB. So this is just a logical representation. the ultimately is stored in a data page. For one table, there can be so many data pages, right? And each data page is stored in ultimately the physical memory of data block, and one data block can hold many data pages, right? And DBMS maintains the mapping also, which page goes into which data block. Okay, till now we are clear. Now let's see the second part. What type of indexing present in RDBMS? Now here if you see that, the things become little, you can say that, interesting. So this name you might have heard a lot: clustered indexing and non-clustered indexing. I know the things which will be going in your mind. Primary index, as soon as you heard a name indexing, you will be like primary index, secondary index, and what is that, composite index. Like there would be so many indexing, so all these things should have come in your mind. But from the indexing DBMS perspective, they are categorized into two types: clustered indexing, non-clustered indexing. So forget about, like, before we understand clustered indexing and non-clustered indexing, first we have to understand what is indexing. When we are saying indexing, but what does indexing means, right? What data structure is used for doing that indexing, how it works, then we can come to that, okay, clustered and non-clustered. But first we have to better understand what indexing is, how it is done. So in a simple term, if I say that what indexing is, it is used to increase the performance of the database query so that data can be fetched faster. Okay, so indexing is just nothing but doing to increase the performance of the query so that it helps us to find the data much faster. Without indexing, DBMS has to iterate each and every table row to find the requested data. So you know that it maintains the data pages. Data page 1, let's say there are 1000 data pages. Inside this 1000 data pages, there are, let's say, 1 lakh rows data, right? Now if you have to find something that, hey, give me data with employee ID 35. Now DBMS doesn't know that which this employee 35 record goes into which data page. It doesn't know. All DBMS has till now is indexing. Okay, this data page goes into this block. So what it can do is that in a worst case, it will iterate over this mapping. Okay, my page 1, it will goes to this physical memory, load the data, load this block into the main memory, take out the rows, read this page and see. It read this page and see that, hey, does employee ID 35 present? No. If it is no, it goes to the second one. Okay, my page 2 store is in this block again. So it is already in memory. So it will load that page 2, right? And then it will again, it's page 2, it will check all its rows. Hey, have I found this employee ID 35 or not? Let's say, for example, worst case, this employee is present in the last data page, the last mapping which is present here. Then it has to iterate over all the data pages, and inside all the data pages, it has to iterate over all the rows. So what is the worst time complexity? Big O of n. So without indexing, it has to check each and every row, right? And if there are, let's say, millions of rows present, query can take some time to fetch the data, right? Because it has to goes to that particular data block from the mapping, fetch the data, load into the memory, read the data page, take out its rows and then read it and see. So we know that indexing is used to make the query run faster. Without it, it would be big O of n. But with it, what would be the best time complexity we can give? So there is a data structure which is used which is known as B plus tree, it provides big O of log n time complexity for insertion, searching and deletion. So this is very frequently used, B plus tree, while for doing the indexing, right? So without indexing, big O of n is the time complexity to search any data inside a table. With indexing, our purpose is to make our searching faster, and which data structure it uses B plus tree, right? So B here stands for balanced actually. So now, till now we are slowly understanding, okay, what indexing is, and for making the indexing works, what data structure is used, B plus tree. It provides a big O of log n time complexity. So before I go further into the clustered, non-clustered index, let's first see how B tree works. It will clear your mind actually how this data indexing works. So I'll talk about B tree. So B tree and B plus tree is very similar, right? So if you understand B tree, B plus tree is somewhere near to exactly same. Okay. So now I am saying B tree, and at last I will say that it is a B plus tree, how it adds certain additional feature, but both are exactly same. So I'm just telling you how B tree works. So it maintains the sorted data. Okay. All leaves are at the same level. M order B tree means each node can have at most M children. For example, 2 order B tree means each node can have at most 2 children. 3 order B tree means each node can have at most 3 children, right? You can have any number of this M order. So you can have, let's say, 5 order B tree means you can have at most 5 children. Okay. And M minus 1 keys per node. So now here if you see that, when I say that, let's say 3 order B tree. So let's say this is the 3 order B tree. So it can have 3 children. So in one node, so in the 3 order B tree, a one node can have 3 minus 1, M minus 1 keys, right? So 3 minus 1, 2. So it will have 1 key here, 1 key here, right? And it will have pointers here. So this is a pointer, this is a pointer, this is a pointer. So this pointer will point to this child node. Let's say this is key 1. This pointer will point to this pointer, child node 2. And let's say this is key 2. And this pointer will point to this one. So in one node, if in 3 order B tree, you can maximum have M minus 1. So 3 minus 1, 2 keys here and 3 pointers. And each 3 pointers can point to a child. So now you can say that, hey, what this 3 pointers generally signifies. So let's see that. We'll come to that part. So now let's say that I'll totally show an example how it will become total clear. Let's store the below data in a 3 order B tree. So 3 order B tree means it will have how many keys? M minus 1, 3 minus 1, 2 keys. So I have here key 1 and key 2. And it will have 3 pointers, pointer 1, pointer 2, pointer 3. So now here if you see that this pointer 1, left 1. So left 1 is like always point to the child node which is less than this key. Less than this key. And the right one is like greater than equals to this one. So this pointer 1 will be whatever the child it will point to, all its data would be less than this key. And whatever this pointer 2 which is on the right side of this key, whatever the child it will point to ultimately, all its data could be greater than equals to this key, right? So similarly for this key 2, this pointer 2 is its at left side. So whatever the child it will point to, it will have a data less than key 2 only. And this pointer will have a, whatever the child it will point to, it will have data greater than equals to, right? So that's why here we have 2 keys, 3 pointers. So that's why one node can have 3 childs. That's why it's 3 order. Maximum 3 child you can have, right? Now let's see an example. Let's understand with an example. It would be super clear. So don't worry about till now what we have understand about this DB, right? Pages and all. So we will come back to again and everything will start making the dots clear. But keep that till in your back of your mind that whatever we have is known till now. Okay, so now let's say we want to store this data into a B tree. Okay, so I am using a 3 order B tree. Okay, so how many? So understand this line is a pointer. Let's say this is 1 pointer, 2 pointer, and 3 pointer, and 2 nodes, m minus 1 nodes. So 2 nodes. So this is the nodes slots I have. So first I want to store 9. So I have a key. So this is the key 1. So I have a space. So I have stored a 9 here. Okay. Now I want to store the data 33. So it always maintain the sorted data. I have a space in this node itself, right? So I have stored in the sorted order 33. So both my keys are now full. So it also has the data. This also has the data. Currently these pointers are pointing to nothing. This is pointing to nothing. Now I want to store 75. So where I would store now? Because in my node, because I am creating a 3 order tree. So in the 3 order, I can only hold 2 nodes, 2 keys. Now where I would store 75. So now what it will do is that in the sequencing order, it is like 9, 33, 75. So what it will do is, it take the middle one and take it to the parent, right? So now what I have done is, I have created a new node from the middle one of this 3 and make it to the parent of this. So now 33 left pointer points to this, 33 right pointer will point to this. So left pointer means less than 33. Right pointer could have like greater than equals to 33 data it will hold. Okay, so till now it's all clear, and this is how the data will look now. Now we want to store 41. So 41 where we will store? So it will first check at the 33. 41 is greater than 33. Yes, it goes to the right side. Now here if we'll see that here 75. So 41. So it will sort this. So it will do 41, 75, and it will see that yes, there is a sufficient space, right? So it will store it. So this is how it will get stored after 41, right? Because 41 is greater than 33, it goes to a right side from the pointer, and then it is stored in a sorted manner. And it has 2 nodes we can keep, so it's okay. Now we want to insert 98. So 98 is greater than 33. It goes to the right hand side. Now it want to store over here. So now again 41, 75, 98 in a sorted form. But again we can't store 3 keys because it's a 3 order B tree. We can only store 2. So what it will do is, we will take the mid one and take it to the parent. So its parent is 33. There is an space. So it will store there, and 75 left will point to 41 and its right will point to 98. So this one is like less than data 75. This one is greater than equals to 75. It will point to. Now we want to insert 214. Now I think you got the point, right? What we are doing. So 214, it will check. where it will go, it will say that okay, it is greater than 75, so it will goes here. Greater than equals to 75, it will go here. There is already a slot empty, so it will put it here in the sorted manner 214. Now let's say we want to insert 126. 126 is greater than 75, it goes to its right, and 98, 217. So this is the sorted how it would look like, but it breaks the B tree because we can't store 3 nodes, only 2 keys we can store. So this has to be mid one. After sorting, it has to take out. So now it has to take to the parent. So 33, 75, 126. 126 left will point to this 98. Its right will point to 214. But here if you see that this parent itself will get break now, because we can't store 3, 33, 75, 126, we can't hold it. So this further has to be taken out a mid one, 75. Now it should has goes to its parent. So there is no parent, we created a new node, 75. 75 left will point to 33. 75 right pointer will point to 126. 33 left is already pointing to 9. It's 33 right already pointing to 41. So it is like this. So you got it right, how B tree stores the data in a sorted manner, and plus we can construct M array or M order of B trees, right? So let's say now I am storing 55. 55 is less than here. It is greater than this. It will go here. There is a free slot. 41 free slot was there, so it will store the 55 here. Similarly for 72, I think you can do now yourself that it will come here, but it will break. It will divide 55. It will take it to the parent, and how it will look like. So this is how B tree works, right? So now you know that balanced tree this works. I might have explained faster because you can learn this data structures more in depth, or you can implement it. But without understanding this, understanding the indexing would be incomplete. So B plus tree is exactly the same as B tree, with additional feature that child nodes are also linked to each other. So in the B plus tree, it has additional feature that these all child nodes are linked to each other. So that's okay. If you understand the B tree, B plus tree is also exactly the same. So now let's come back again to our DBMS. DBMS is using the B plus tree to manage its data page, because I told you that for one table, if it is a, let's say 1 lakh rows, it can have so many data page. Data page 1, data page 2, data page 100, let's say. And inside each data page, there will be hundreds of rows. So there might be some kind of ordering, right? How to order those, right? So that's where B plus tree comes into the picture. DBMS uses B plus tree to manage its data page and rows within that pages. How? Okay, so just have this like it is using the B tree exactly the same, only with slight differences. The root node or intermediate node holds the value which is used for faster searching the data. Possible that value might be deleted from the DB, but it can be used for sorting the tree, right? Leaf node actually holds the indexed column value. Don't worry, I'll tell you what I mean to say that what DBMSs do. We will see that. So what I mean to say is that here is, so here when we are maintaining the B plus tree, ultimately the leaf node, this leaf nodes actually holds the index values. So let's say this is the column. In this column, I want to put an index. So this is the index column. So what is the index value? 19, 25, 30, 17, 6, 1, 5. So these leaf node are actually the one which hold this index values. The root node and the intermediary node, this root node and intermediary node might store some data, let's say 32, which might even not even there. Earlier it was there, but it might have deleted. It's not even there now. So it is possible that it might be present here into the root node or intermediary node, because they just help us to do faster searching, go left, go right and all. But this leaf node actually holds this current values of the column which is indexed, right? That's what I meant to say. Okay, so now let's see how DBMS is actually using B plus tree to maintain the data pages and indexing. Now let's say this is the table, very basic table, right? How many rows? 1, 2, 3, 4, 5, 6, 7. 7 rows are let's say are row 1, row 2 to row 7, right? And we have two column 1, column 2. Very basic table. Now I have put an index on employee ID. I have put an index on this employee ID. So we know that whenever we are putting an index, now DBMS will apply B plus tree on it. Apply what? B plus tree on it to sort, to manage this data. How? Right? So exactly the same way which it has done, exactly the same way it will do this. So now this is the column where I have put the index. Now it will read this 19, 25, 30. So now it will start creating a B tree out of it, right? So what before even, so don't look at this pointer now, right? I will explain you. But now see this, first is 19. So you know that I am still using the 3 order. So in 3 order means how many, one node, how many keys you can store? M-1, which is 2, right? So, and there how many pointers would be there? 3 pointers would be there, and 2 keys I can store. So 19. So in the key 1, I have stored 19. Okay. Don't forget about this pointer now. This pointing to data page and all. Forget about this. Let's first focus on this construction of a B tree. The second is 25. So now the second row is coming 25. So the key 2 was empty. So I have put 25 into this part. Third one is 30. So now if I put 30 here, it will break because it's a 3 order tree. In one node you can have only 2 keys. You can't put 30. So you have, after sorting whatever the mid one is, you have to take it to its parent. So it would look like this. So there were no parents, so I created a new node. I put 25 there. 25 now left pointer will point to 19 and its right pointer will point to this node, which holds 25, 30. So now this is the first difference you should notice. I told you, right, in the DBMS, when it used B plus tree, leaf node actually holds the index column value. These are the index column values, right? So leaf node stores it. The left pointer holds less than 25. Right pointer stores greater than equals to 25. So here if you see, I have put the 25 here also. I have put the 25 here also because in the leaf node itself, we hold this value. In future, it is possible that 25 row is deleted. So I might delete this, but this could still be there. This is an intermediate node. This is just for faster searching. Anything comes, he goes to right. If this right, you will find values greater than equals to 25. But this doesn't signify that this is the index column value in the DB which is stored. No. Okay, got it? So this 25, right, we have to put greater than equals to 25. So we are storing the 25, right? So 25 would be stored here and 30. So in a sorted manner. Then what we have to store? 17. So in this 17, where it will go, it is lesser than 25. It goes to the left side of it. 17 is lesser, so it will go to this. There is already one space present, so it will store in a sorted manner. So 17 first, 19 later. After that 6. Where the 6 will go? So 6 is lesser than 25. It will goes there. Now there is no child, so generally 6 would be in the first of 6, 17, 19 sorted manner. But again, 3 keys we can't store over here. We have to now divide. Take a mid one, take it to the parent. Who is the parent? 25. So it will in a sorted manner 17, 25. 17 left will point to 16. 17 right, because this is a still have the index value, right? So it will point to 17 and 19, greater than equals to 17, 17 and 19. And 25 right will point to its 25, 30. So you see that 3 child it has currently, each node. Then we want to store 1. So 1 is less than 17. It goes to left. So there is one space. So it is stored in a sorted manner 1, 6. Similarly the 5. So the 5 lesser than this. It goes here. So generally the 5 should be here in between of 1 and 6. But it will break. So 3 keys we can't have it. So it should goes to the parent. Right? If 5 goes to the parent, the 5 left would become 1. 5 right greater than equals to 5. And it's a key also, so 5 should also be there. 5 and 6. But at the parent level, you can't have 3 nodes, right? So again, the mid one, 5, 17, 25, again it has to go to the top. So it's hold 5, it's right hold 25. Now here if you see that I am not putting 17, 25, right? Because this is just an intermediary node. Intermediary node, I told you that it is not index, column index values. Column index values are only the leaf, right? So I am only changing the intermediary node. It's going top. So that's why I don't have to put 17 here, because it's not index, column index value. So 17 right will point to 25 and this thing. So graph will be, so this B tree is constructed. So now here if you see that at the bottom, this bottom part, this is now sorted. So here we have a mixed data. But bottom what we have now of this B tree is 1, 5, 6, 17, 19, 25, 30. See? Sorted. Right? Now we understand that, okay, how whenever we make any column index, DBMS do B plus tree on it. But Shreyansh, how the data pages are created? Now, how it gonna link? Because you told that one table can have 100 of data page 1, data page 100. How those gonna manage, right? So because these are actually has the row. So what till now I have understood is, okay, DBMS has so many data pages, data page 1, data page 2, like this. Each data page is stored in a data block, and one data block can have many pages like page 1, page 2. Data block can have certain, let's say page 5, page 6, something. DBMS maintains the mapping of page 1, block 1, page 2, let's say again block 1, like this. It mapping it does. I know that whenever any column is indexed, right, it maintains a B tree. You now understand how B tree is constructed, so that the data of this column is now in the sorted manner, But now we need to connect the dots. So now B tree exists. I understand this. I know data pages. I know data block. But what is the dots connecting to all of this? Now let's understand this. Okay. Now let's understand this. Our table has empty. And we are inserting the row from start. Right. So now let's say we have make this column indexed. And now only first row is inserted, 19E1. This is the row. I told you now that first what DBMS will do, it will create a B plus tree, right, for this data also. So it will put 19. Now remember, in DBMS with this key, it will also hold one more pointer value, or you can say that the pointer with this key is, which ultimately points that this belongs to which data page. This 19 is stored in which data page. So now let's say I told you that this is the first time we are creating a table. This is the first row. So data page is currently empty. So I created a data page 1 and stored one row 19E1 and put a pointer here that okay, this 19 is points to this data page 1. And let's say this data page can only hold 3 rows. Okay, so when I put 19, so DBMS ultimately, actually this is just our representation. DBMS what ultimately has done is it created a data page 1, stores in this 19E1 row. It created a B tree on this index column. It also maintaining the index, put a 19. With this 19, it also maintains one more pointer that this 19 row belongs to this data page. And also this data page ultimately has to be stored in some memory or data block. Let's say it is stored in 1. So it is also now storing this data page 1 data block stored in 1. So this is the data page 1 in the disk. Okay, so now second row is inserted. So when second row is inserted, it is inserted where? In the data page first. So data page second row is inserted because data page can hold 3 rows. It is only the second row, it inserted properly. Now it will update its indexing because new row is inserted, right? It has to update its indexing. So it will check that okay, one node is free, one key is free. So it will put 25 here. And also manage one more pointer with it, and this pointer that 25 is stored in where? Data page 1 only. It put this pointer in which data page this 25 holds, this record holds, right? Till now data page is in data block 1 only. Now 30. So when 30 is stored, so first it will store in the data page 1 only, right? So because it has the space, right? So you can say that first what it will do is it will try to see that which data page it has to pick, right? So one more question it has to comes to your mind that, hey Shansh, if there are so many data pages already exist and when you inserting a new row, let's say we are inserting 30. This is data page 1, data page 2, data page 100. Which data page to pick and insert? Which data page? Right? This is a very interesting question that whenever you are insert a row, which data page you will insert it. How DBMS knows it? So this is how it knows is through B tree only. So when I inserting a 30, so first it will goes that tries to insert a 30 into the tree, B tree. So it will see that okay, it will try to construct a tree. You already know that how we did it. So ultimately it gonna be look like 19 and here 25, 30. So what it will see is that hey, my nearest index is stored in which data page? 25 was stored in data page 1. So what it will do is DBMS will try to check the data page 1, right? So from its data page 1 memory, it will check out its mapping database 1. It is there in the data block 1. It will load it, right? And what it will put is this row and put it back into the data block, right? And one more pointer it will store with 30 is that it is stored in data page 1. Got it? We will see one more example. Now let's say 17 I want to store. Now which data page? So let's say if we have so many data pages, which data page it has to pick? How it will determine? First it will go into this B tree. It will try to find out the correct logical sequence of this 17. So 17 is less than 25. It goes here. There is a space available. So it will store here. Now it will check its neighbor index that which data page it is stored, and it pick one of the very you can say that one of the data page. So 19 is stored where? So 19 is stored in data page 1, right? So it will see that, okay, let me pick also data page 1. So what it will do is DBMS will pick the data page 1. So data page 1, it knows that it is stored in data block 1. It will hit the, goes to the memory, load it. From the data block 1, it loads the data page 1. Now in the data page 1, we already know that it is full. 3 data it already has. It cannot insert 17. Now what to do? Now what it will do is DBMS will do page splitting. Page splitting. So now in the page splitting, it will split or create one more page. So it will create new page, page 2, right? And it will split the data. So earlier page 1 has 19, 25, 30. Now 17 it has to store, and now it will just split the data. So now let's say in page 1, it puts 17, 19 rows data. And in the page 2, it put rest of the data, whatever the page 1. So page 1 has this 3 data, right? 19, 25, 30. So whenever it pick a particular page, so it picked page 1. Page 1 has no space. So now the page splitting happen. So in the page splitting, a new page is constructed and it divide the data of the page 1 plus this new data, right? So 17, 19 I have put into page 1 and 25, 30 I have put here in the page 2, right? It can be anything depending upon the DBMS, and it will update the pointer. So now 17 will point to that it is in page 1. 19, it will update its pointer that it is also in page 1. Now it will update the pointer. 25 is present into page 2. 30, it updated that it now is present into page 2. Earlier 30 was present into page 1. So it has to update the pointer. So it will update the pointer that this index value 30, its all corresponding data is present into page 2. And also it will maintain a mapping that, hey, this page 2 is stored in, let's say, data block 1 itself. Okay. Now, what data we have to store after 17? Let's say 6. So it will try to insert a 6. 6 will go here. Okay. So first it will try to identify its correct logical location. Okay. So it will find out it's that, okay, 17 has to be go up. It find out its correct location. Now it will check its nearest neighbors, nearest index in which data page it has. So nearest, it's all are linked in B plus tree, I told you, right? So it will check that, okay, this 17 is stored in page 1. So what it will try to insert the 6 into page 1. So DBMS will load the page 1. So from the physical memory, it goes to a data block 1, loads the page 1. Page 1 has now these 2 records. It will insert the page 1 already has 17 E4, 19 E1. It will store the 6 also, because 3 we can store. So it will store 6, and 6 data is E5, right? And it will update the pointer of this to that it is stored in page 1. Similarly for 1 also. So ultimately 1 goes here. Now here, can you tell me 1, when it goes to the 1 will see it to its neighbor. Hey, which data page you are stored in? 6 will say that, hey, I am stored in data page 1. So DBMS will try to insert the 1 into the data page 1. So it will load the data page 1. It can easily load it that it has that data page 1 is stored in block 1. So now it will store page 1. Page 1 already has 3 rows. It is totally full now. 17, 19, 6. 17, 19, 6. And its data. E4, E1, E5. E4, E1, E5. Some data is already there. Now it tried to insert 1, but you can't insert 1, right? It's already full. So what will happen now? Page splitting. So it will create a new page. So page 2 was already there. So it will create, let's say, page 3. It will now split the data. So let's say it 17, 19, it will keep here. And it will put, let's say, 1 and 6 here. 1 and 6 here. Right? And it will update the pointer. So 1 is now pointing to page 3. 6 is also now pointing to page 3. It has to update the pointer. Earlier 6 was pointing to page 1. Now it has to, after splitting, 6 has to point to page 3. Right? And also it will add a new mapping also, that page 1 is there in block 1. Page 2 was there in block 2, block 1. Now it will have the, let's say, page 3 goes into, let's say, block 2 somewhere. While storing into the memory, it knows that in which block it goes. So it does the mapping. Now, does everything making sense to you? That how everything is linked? Right? One thing I still haven't tell you about this offset array. How this offset array is used. I will tell you when I tell you about clustered, non-clustered. But till now, tell me that in the comment section, is it clear to you? I am going very slow. You know, right, how the table data is actually stored in a page. There can be, this page ultimately get stored into data blocks. So DBMS has to maintain the mapping, page versus block. Right? Then for indexing, B+tree, I think it should be clear to you. We have seen with an example. So whenever we insert a row, it first put its logical ordering into the B tree, determine the best page it has to be stored, because there can be so many pages. Determine the best page where this data has to be stored. Right? So we have seen an example that where the logical ordering is, it check its neighbor, it tried to load that page and see if that can be accommodated in that page. If not, page splitting happen. Whenever page splitting happen, a new page is created and it just split the data. Right? And it has to update the pointers also. It might be possible that earlier this neighbor node 25, let's say, was storing into page 1, but after splitting, 25 goes into page 2. So this pointer has to be updated. And whenever any new page is stored, in whatever the data block is ultimately inserted, DBMS has to maintain the mapping. Clear till now? Cool. Now let's come back to the indexing part. Hey, what is the two type of indexing, clustered and non-clustered? Now I know that how DBMS actually does the indexing. But what are these two type of indexing? So see, first let's understand the cluster indexing. Cluster indexing says that order of rows inside the data page match with the order of the index. Order of rows inside the data page match with the order of the index. Let's see with an example what I'm trying to say. So let's say this is the table. 1452 ACBD, and this is the address. Okay, so I told you at first that in the data page, whatever the sequence in which the rows are inserted into a table, generally in that order only the rows are inserted into a page only, right? So if you are creating a employee id 1, so here in the data page, this row will come first, after 4, then 5, then 2. Now let's say I have put an index over here. Now you know that when you put an index, DBMS will do B tree on this index and it will have this sorted 1, 2, 4, 5. Now you know that, right? How 1, 2, 4, 5, this at the base it would be in sorted only. And 1 will also hold a pointer to this. So when we say that, right, 1 will hold a pointer to this one row. How? Ultimately, actually, this one will hold pointer to this page in which this row is present. Right? Now, here the sequence, indexing sequence says that 1, 2, 4, 5. And in the page, order is 1, 4, 5, 2. The way it is inserted, rows are inserted 1, 4, 5, 2. But hey, you are saying that the order of rows inside the data page match with the order of the index. That's what clustered indexing says. How we maintain the order? Because you are saying that the order of the rows which are inserted in a data page is depend upon how we inserted actually. Right? So we inserted 1, 4, 5, 2. So it is stored like this 1, 4, 5, 2. But indexing on this column, indexing is in sorted order. So it should be 1, 2, 4, 5. So the order of the rows should be 1, 2, 4, 5. How? That's where the offset comes into the picture. I told you that in offset it maintain an array. Right? And it has an array like 0, 1, 2, 3. So whatever the indexing or you ordering is, so indexing ordering is 1, 2, 4, 5 sequential. So at index 0, it would point to employee ID 1 data. So it will point to employee ID 1 data. Then after that 2. So index 1, it will point to employee 2 data. 2 data. So third would be 4. So and the next in the sequence of the array would be 4. So now you see that even though the data pages, the rows inside the data pages are jumbled or depend upon how the user might have inserted, mixed mode. After indexing, whatever the sequence comes out, the order is generally given by the offset. So whenever you will traverse this pages, you will traverse in this sequence of this offset. So at 0th slot, it is employee 1, then 2, then 4, then 5. 1, 2, 4, 5, like sequencing. Understood that the useness of this offset, it holds a pointer, and that's where cluster indexing is, that the order of rows inside the data pages match with the order of the indexing. So it doesn't mean that this rows are sequencing is changed. This offset is changed. This offset array holds the data in this manner so that it maintains the indexing sequencing. Okay. So there can be only one clustered index per table. Why? Because you can create an order of a rows based on one index only, right? So now let's say this is employee ID. Let's say name. Can a clustered index can be made on two, employee ID and name, A, C, D, B. Let's say index is, let's say for this A, B, C, D, right? But in the cluster index, the order has to be maintained. So order can be maintained either through this or through this. So that's why there in a DB, in a one table, there can be only one cluster index. So what column can be a cluster index? So it give a first priority to the primary key. So in this table, let's say if I have created an employee ID as a primary key, DBMS used this as a clustered key. And whenever it use it as a clustered key, it will sort the data pages based on that one. Whatever the index comes. So based on this clustered key, it creates a B tree, B plus tree, and whatever the B plus tree, ultimately the index sequence comes, the data pages also it will insert in the same manner. Like not this offset, the offset it will maintain in the same manner. Right? So first priority it will go to the primary key. If manually you have not specified any clustered key, then DBMS look for primary key which is unique and not null, and it is used as clustered key. But let's say your table doesn't have primary key. Then what? What will happen? How DBMS will create a B plus tree out of it when you don't have the primary key? Internally, which is not visible to you, DBMS create a new column. And it is generally sequential incremental 1, 2, 3, 4, 5, 6, 7, right? With every row you insert. So it created as a clustered key and store the data pages based on this. So any new row you will insert, it will add. So this is auto increment column. It insert which is not visible to you. It is used as a cluster key. So it used that value in a B plus tree to determine which data page to pick, where to put, what would be the offset sequence for that page and all. Now you can ask that, hey, what if, let's say I have a big table. I have, let's say, 1 million rows, but I haven't defined the primary key. There is no primary key. So what happened would be DBMS internally creates a new auto increment column and does a B tree out of it and maintains everything. It maintains page 1, page 2, page 1000, data block 1, data block 2, anything. Whatever the mapping it has been doing, it is doing. Even the rows ordering also it is doing. But now you can ask that, hey, what if after now I added a primary key and make one column as a primary key? So now as soon as you make a primary key, I told you this will get priority. So now DBMS has to do lot of work. It has to regenerate this B plus tree. It has to update all the pointers now based on this new index column. It has to update the B plus tree pointers. It might have to load so many data pages out of the block, reshuffle the rows, right? So lot of work DBMS has to do, but everything has to be changed now based on this column indexing. Okay, so that's what it is. If a table there is no primary key, then internally it creates a hidden column which is used as a cluster index. This column just increase sequentially and guaranteed unique and not null. So cluster index, you already got it, right? It actually based upon this column, which is, you can say that the primary key column, which is always generally considered as a clustered key. It orders your rows and pages based on that. Then you can say that, hey, what is non-clustered key? Okay, clustered key take care of primary key. But you remember, we have so many other keys also. Secondary key, composite key. What about those? So, or let's say that I have a scenario where this name can be used a lot to query. So it is better to put the indexing on it also. So non-clustered is like I can put indexing, or you can say that non-clustered indexing I can put on this name, secondary index. So on the name also I can put an index. Let's say I'm putting an index on name also. But now this name would not be considered as a primary key, or it's a secondary key, let's say. So whenever you are creating a secondary key, composite key, right? Ultimately it is doing non-clustered indexing. So what does it means that, so now let's say I'm doing name. So based on that b plus tree on the name, let's say it is able to maintain certain sequence, that this is A, this is B, let's say this is D, this is D. Okay, this A. Now what? So now two things. So it will again, this A data is stored in where? Let's say in page 1. So it will point to the page 1. This B is stored in somewhere. So, but here if you see that the ordering of this offsets are not based on this first, correct? The ordering of this, I would say that the ordering of the rows doesn't depend upon this secondary index. Second, there can be many secondary index or composite index. So I can have address also as an index. So it will create one more B tree and stores the data and just maintain the pointer to the database. Right? So we have only one clustered index. This clustered index actually drives this ordering of this row. And we can have many secondary index or the non-clustered index. As your name says, that clustered, you are not clustering the rows and pages, right? So we can have many non-clustered index or secondary index, right? And that's one of the reason when somebody asks like, you should always create index. You can say that we should not, like, I have 10 columns, let's say. Column 1, column 2, column 3, column 4. You might be asking that, hey Shreyansh, why can't, so this is primary key, why can't I put this I will also make secondary index, this is also I will make secondary index, this is also I will make secondary index. Or like whatever the query will come, it would be faster. Now you understand, at least grasp that there is an overhead. So for each secondary index, you have to maintain a B plus tree for it. Now, if there are 1 million rows in this table, let's say 1 million rows, means in a B plus tree, you are creating so many keys here, right? You can just consider the amount of memory it also required, right? Let's say if you have 3 secondary index, so means you are creating 3 B plus tree, like a non-clustered index 1 for this secondary index for this column 2. You might be creating another B plus tree for non-clustered index, indexing you might be doing for column 3 for again 1 million record, like this. Now assume that any row, particular row is deleted. You have to update the pointers also of this. You have to delete that row, or because this is the leaf node has the index value, you have to delete that node also. And when you delete it, you might have, it might be possible that you have to update the pointer also. So that's why it is always say that create an indexing carefully. It is not easy, because there is a lot of overhead comes in. What are the overhead? First thing is, this B plus tree also needs memory. So you have to worry about the memory also, because this is also ultimately going to store in the disk only, right? And it DBMS also, whatever the data it is stored, it also stored into pages which is known as index pages. And this index pages are stored in disk only. So there is a overhead that it maintains the index pages. So because I told you that 1 million nodes it created, Definitely 1 million node cannot comes into one page. It might have to create so many index pages also. Index pages also comes into so many, let's say block 5, block 6, block 7. So now you see the overhead which DBMS has. It has to maintain the index pages also. Index pages mapping also. It has to maintain the data page where the data is actually stored, and its mapping also blocks. So just creating a secondary index, composite index, and indexing will just create an additional overhead. And any addition, because anytime you add a new element, you have to update your clustered index, the primary key one. Then all the secondary you also have to update. And in the update, I already told you, page split can happen. When the page split happen, it might divide, right? So index has to be updated. So I think it's pretty much clear, right? So now you know that what all things has to be done. So whenever you have to, it looks simple, right? So whenever you have to insert one row, new row, what all things it does, right? It first find an index page, right? What would be the first step? It first find the index page, right? So in from the index mapping, index page 1, index page 2, let's say block 1, block 2. So it will first load the indexes pages into the memory, right? Because indexes pages has your B tree data combination indexing, right? So second, what it will do is, or you can say that, so let's say, or I would say that instead of inserting, let's say you want to search, because we are talking about search query. So let's say you want to search a data with 35, let's say I'm saying ID. So first it has to load the index page. Index page is loaded from this data blocks. Now from this index pages, it will run the B plus tree. It will traverse this B plus tree to find which data page this 35 has. So maybe you have a data page, this indexes has the data. So now let's say this 35 ultimately points to a particular data page 5, let's say. So now for second step is using the B plus tree and find the data page. Third step, use that data page, find the data block. It maintain a mapping, right? Data page, which data block? Let's say 2. So now it can directly goes to that data block, load that data block in memory, right? Fifth, read the data, right? So now even if there are hundred thousands of data block, it doesn't have to worry. It can directly goes to that particular data block. Okay, so this is, check it out one more time. It would be a little bit clear, but this is, so many things happens, right, in the background, and we can discuss more if you have doubt in the comment section. And even if you wanted, I can have one live session where we can discuss more. Okay guys, thank you, bye.